Hi everyone. Today we shall see non-additive or lossless join property of a relation which is decomposed into n number of how to design a database. We begin with a universal relation and identify the functional dependencies, and subsequently we apply the first normal, second, third and fourth normal forms to decompose the relation into smaller relations which have desirable properties. However, in the process, we may lose some of the functional dependencies which were present in the original relations, or we may end up with relations though have desirable properties, but when you take a join, they may generate spurious tuples. So if our decomposition is right, then even after joining, there should not be any spurious tuples generated. So such relations are called as lossless or non-additive decompositions. So let's look at some of these definitions to begin with. So let's see what is meant by a lossless or non-additive join property. So if you look at the definition that is given here, a decomposition D comprising of several relations R1, R2 up to Rm has lossless join property with respect to a set of given functional dependencies F if for every relation state R of R that satisfies with F, the following condition holds. That is, the natural join of all the subrelations should result into original relations. Assuming that we have n relations along with their states. So let me change the color here. Yeah. So let us assume the states of individual relations are R of R1, R of R2, up to R of Rm. So the decomposition D comprises of M subrelations and their respective relation states are R of R1 and so on. So if the universal relation R were to comprise of all the attributes of R1, all the attributes of R2 and all the attributes of Rm, this R would have its own state R of R. So if we take natural join of all these subrelations, we must get the original relation state. So if this condition is satisfied, then we say that the decomposition is lossless or non-additive. So please note both things are same, non-additive and lossless. Okay. So we have seen the definition of what is non-additive or lossless join property. In the exam, the question would be define what is lossless or non-additive join property. So you should be able to define this non-additive or lossless join property with an illustrative example like this. So having looked at what is lossless join property, is there an algorithm which will help me to find out whether the given decomposition is lossy or lossless? So that particular algorithm is described here. So testing for non-additive join property. Now this algorithm is slightly involved and requires an example to be used to illustrate the concept. So before we take on the example, let us look at some of these steps that are given here. So what is the input for this algorithm? The input for this algorithm is a decomposition D with its individual relations R1, R2, Rm and a set of functional dependencies. So there are two inputs. One is the decomposition set D and a set of functional dependencies F. So how does the algorithm begin? The algorithm begins by creating a matrix S. So you have to create a matrix S. Then the size of this matrix is decided by how many decomposed relations are there. So if there are M decompositions, then there would be M rows in the matrix S. So we'll have R1, R2, R3 up to Rm. So number of rows is decided by the number of decomposed relations. So this is my number of rows in the matrix S. And how many columns are there in this matrix S? It is equivalent to all the attributes which are there in R1 to Rm all put together. So it is A1, A2, A3, A4 up to, let us say, An. And some of these attributes may appear in more than one subrelations. That is perfectly fine. So first thing to do is you have to create a matrix of size m by n, where m is the number of decomposition and n is the all the attributes in the universal relation R, which is made from all these subrelations R1 to Rn. Okay. Now that is the first step, and you have to say in the second step, for each element ij, you have to put bij. It means you will put b11 here, b12, b13, b14, somewhere here b1j, and up to b1n. Similarly here b21, b22, like this b2j, and up to b2n. So likewise you should have bm1, comma bm2, bmj, and then here up to bmn. So this is the initial matrix that you would create. The next step is for each row I representing a relation Ri. So you go to first row here, I is 1, and if attribute aj is contained in Ri, then you have to replace that particular bij value with aj. For instance, if R1 contains A3, you are going to replace this by AJ, which is A3. Okay, and if R1 contains A1 also, then you are going to replace this by A1. So whichever attribute is found in R, that will be replaced by AJ in each of the rows, taking each RJ at a time. So you have to go through each of the subrelation and see if any of the Bij is to be replaced by Aj. That is the third step here. The next step is interesting, where you have to apply the functional dependencies. So you have to repeat a loop until executions results in no changes to S. Until no changes happen in S, you have to keep on doing the step number 4. So what you have to do in step number 4? Remember, we are given as input the functional dependency set also, which contains functional dependency of the form x or y in. Okay, now for all rows in S that have same symbols in the corresponding attributes of x, so what you have to do is take each functional dependency of the form x or y, and x may contain some attributes, let's say a2 and a3, and this could be a5 or something. Now what you have to do is, for all rows in that have same symbol in the column corresponding to x, okay, so suppose in the column x, that is a2, a3 here, you have to check if any of the rows contain same values in particular row. For example, R3, if we have A2 here and here we have A3, so you will see that R3 has A2, A3, and you have to find out any other row which contains A2, A3 here. So possibly two rows may contain the same set of values, and the corresponding y values you have to identify. That is in A5 somewhere here. If this particular row contains an AJ, that is A5 here, and this is still B I5 or BIJ, then this BI5 has to be replaced by A5. So you have to cut this and put A5 here. So do this only if the values in the X column match for two rows in a matrix S. And if one of the values A here and other value is B, you have to replace that B by A. Now you have to keep doing this for every FD until no changes happen. After you have done all this, what is step number 5 then? Now in step number 5, you check if any row, if a row is made up entirely of A symbols. So you have to have one row at least with one row at least with all A's, irrespective of their suffixes here. So then the decomposition has non-additive or lossless join property, otherwise it does not. Okay, so this is a complete procedure. I'm sure it's difficult for anyone to understand it fully. With an example, we'll try to illustrate. So let's come to the example quickly. As you can see here, we are given a universal relation R and its decomposition D. So D has three subrelations R1, R2 and R3. So let us form a matrix S. So how many rows are there in this matrix? There will be 3 rows, as many as number of decompositions. And how many rows will be there in this matrix? Equal to the total number of attributes in the universal relation. So R would be given to you. So the first column here is SSN. Second is E name. Third one is P number. Fourth one is P name. Fifth one is P location. And last one is hours. So as you can see, there are 6 columns in this particular matrix. Okay. So there are 6 columns and 3 rows. So what you have to do as a first step, we have to fill every element with Aij, B11, B12, B13, B14, B15, B16. Similarly, here this will be B21, B22, B23, B24, B25, B26. I'm sure you are all following what I'm explaining to you. B31, B32, B33, B34, B35, B36. Don't worry, if you practice a little bit, this will become automatic with you. You can quickly fill up all these things. So we are done with the first step of the algorithm. We have constructed a matrix S comprising of Bij's. Now what we have to do next? Take each relation Ri and check if that attribute is what all attributes are appearing. So we have SSN and E name. Okay, so you have to go and replace that particular Bij with Aj. So this I would replace with A1 because J is 1 here. E name, it is A2 because J is 2 here. So this is the result of application of step number 3. Then you have to pick up the next row, that is R2, and check which attributes are appearing. The corresponding Bij should be replaced by Aj. So P number has to be replaced by A3 here. P name is to be replaced by A4 here. Then P location is to be replaced by A5 here. As you can see, each of the Bij are now turning into Ajs. However, no row has all A's yet. Now, third row here, or the third decomposition is verbs on, which is SSN. SSN, again, this has to be replaced by A1. Then P number, which is A3 here. Then hours, that is, this should be replaced by A6. So let me rewrite this matrix S now with all new values. A1 here, A2 here, B13 it has not changed, B14 has not changed, B15 has not changed, and B16 not changed. Then we have B21, B22. Here it has changed, of course, A3, A4, A5, B26. The last row is A1, B32, A3 here, B34, B35, and A6. So application of step number 3 has resulted into some B's converted into A's. But however, we have to follow the next step, which is very important. Take each functional dependency X or Y, for example, SSN ename. Under SSN column, this is what is SSN column, you find out any two rows which have same A value. So you'll see that R1 and R3 have same A values. And what is the corresponding Y here? Assuming this to be a form X or Y, Y is ename. That is the second column here, which is ename. As you can see, these A's are matching here. The corresponding B's are not matching. Here it is A2, here it is P32. So if A's are there in the SSN column, the corresponding values in the ename column should be altered. So this should be replaced by A2 because there is a functional dependency from SSN to ename. So this is a change that has happened because of application of the first functional dependency. Take the second functional dependency, P number. So P number is the third column here. You identify two rows where A's are same. So you will see that these two are same. What is the right hand side? P name, P location. P name, P location. So you will find that this row has A's here, but the corresponding row under the same column has B's, but the left hand side is same. So you have to replace this by A4 and here with A5. Okay. Once you apply this functional dependency, you will see that the last row has all A's. So you are done. You don't need to apply the last functional dependency anymore. At least one row has to be all A's. So now R3 row has all elements with A's. So this decomposition is lossless or non-additive. Okay, so this given relation is lossless or non-additive. Okay, hope you understood the concepts. You go back and rework on this example. I'm sure you'll all be able to solve this very easily. So thank you for watching. If you like my video, click on the like button and subscribe to my channel. Thank you.